converges in both Newtonian theory and general relativity tidal forces, you only have to know what is happening nearby. It's quite different. It's velocities that's the problem. There is one okay solution. The effect converges if the universe has compact or finite space sections. Then your integral does no longer diverges. Now, as I've mentioned to you before, this is necessarily true if k is +1, you have closed space sections. It can be true, as I've told you also, if you have k is 0 or -1. You can have finite amount of matter in the universe. The integral converges. And so, in fact, compact space sections are preferable. They are much, much better from the viewpoint of local physics than non-compact ones, because then the effect of the distance universe on local systems can be determined, and it's finite. And this is why Albert Einstein was so keen on universes with k is +1. In a sense, it's why he derived his initial model of the universe, was precisely in order to get a universe with closed space sections where everything would converge. Compact is therefore good. Small universes, where we have already seen right round, are even better, because then we can see all of the matter which is causing acceleration here in those universes I discussed with you before, and then we can actually do the calculation properly and really get a good theory of local velocities. Are small universes true? Possibly. They can provide an explanation for the lack of power of the cosmic background radiation in the quadrupole domain. That's a controversial issue, but it's a possible issue. And just one further point, actually, through the same kind of reasoning, in fact, the lumps outside the pass light cone influence the light cone and can in fact have an effect on the cosmic background radiation. This was pointed out by Grischuk and Zeldovich in 1978, talking about the effect of superhorizon inhomogeneities on the cosmic background radiation, impacting the power spectra at low multipoles. And there is a recent paper, Castro et al., Astro PH 0309-320, which discusses this in detail and shows how we can therefore conversely use the cosmic background quadrupole to constrain inhomogeneities outside the visual horizon. Now, you must immediately ask yourself, in this case, well, have they taken that far enough, or should have they gone further and further? And that's an open question which I haven't yet got the answer for. Okay. Next is Machs Principle. This goes back to Ernst Mach, the famous philosopher who heavily influenced Einstein. And actually it goes way, way back. It goes back to Bishop Berkeley and other people. And the question they were asking is, what is the origin of the inertia? Now that's a question that you have to be a deep thinker to ask. What is the origin of inertia? And what Mach and Bishop Berkeley and other people suggested, inertia may be due to the interaction of local matter with very, very distant matter. Now, why should we think that? It goes back to something Newton did many years ago. Newton talked about a rotating reference frame and the origin of centrifugal and Coriolis forces. And Newton believed in absolute space, whereas Berkeley and Mach proposed the relative motion of matter. And what were they trying to explain? First is the bulging of the equator of the Earth. The Earth's equator, as you know, it's not a perfect sphere. It bulges out because the Earth is rotating. Well, the question is, relative to what is the Earth rotating? And Newton suggested it was rotating relative to absolute space. But Berkeley and Mach said, no, the reason for the bulge in the Earth is because the Earth is rotating not due to relative space, but due to distant matter. And from the discussion I've just been giving you, you can see why this could be a possible explanation. The distant matter, the total effect of distant matter, could be very important nearby. And Newton had his famous bucket experiment in which he said, do the following. Take a bucket full of water and twist it with a rope until the rope is highly twisted. The bucket is stationary, the water is stationary, and the surface of the water is flat. Now let go. And the twisted rope starts spinning the bucket. The bucket then communicates that rotation to the water. It settles down in a steady state, and you will find that the surface of the water is curved because of the centrifugal force, as is indicated there. So the rotation of the water gives you that curve. And the key point is the following. In which frame is there no curvature? And the answer is in that frame in which distant stars, as they said then, are at rest. Nowadays we would say the frame in which very distant galaxies are at rest. So the frame in which there's no such dip is the same as the frame in which very distant galaxies are at rest. Now that's a coincidence, unless you can say there is a causal link. And the causal link could be that, in fact, it's the distant matter which is causing the inertial properties of matter. So Ernst Mach said there's no such thing as absolute rotation, there's only relative rotation. And so he contrasted the following. Consider the situation we've just had where the stars are fixed and the bucket is rotating. Contrast that with the situation where the bucket is non-rotating, but the stars as a whole, you're rotating the whole universe around in a huge, huge vortex, if you like. And Mach said, physically, that situation is indistinguishable from that. Here we will get the dip in the water. He says, because everything is relative, it's only relative that counts. In this case, too, you should find a dip in the surface of the water. So that's what Mach said. Now, that's a guess. It may or may not be true. Einstein was heavily influenced by this. And it was one of the major things which led him to general relativity theory. And Einstein initially believed that general relativity would incorporate Machs principle, that it did incorporate Machs principle. And what Einstein believed was through the Einstein field equations, what you ought to be able to show, if there's no matter, there will be no space-time. That was the idea, because you see, through the whole link of general relativity, where inertia and gravity are the same, and they are caused by the space-time metric causing the connection. Basically, the idea was that inertia is caused by the space-time, and that what ought to happen from the Einstein's equations is if you found a solution without matter or without singularities, which represents the limit of matter, there should be no space-time. And he thought that was the case for a long while. It turned out not to be true. Dennis Sciama produced a vector theory of gravity to model this, because that was easier to deal with than the full thing. And in his vector theory, it is indeed true that distant matter dominates and causes local inertia. In his case, the gravitational forces arises from stars' acceleration, decreasing as 1 over r, and the contribution from the distant layers increases and dominates. It's not like, in this case, in Professor Sciama's theory of inertia, which was a very interesting theory, it generated a lot of discussion. It's the more distant ones are more important than the local ones, because you have a 1 over r there. And so, in fact, in this very famous paper, he shows that in that vector theory of gravity, it is indeed the very distant matter which is most important in causing inertia locally. Now, what's the true situation today? Well, there's a total disagreement. The experts still don't agree on the situation. Julian Barber, who writes about it at Loss, says Machs principle is fully incorporated in general relativity. Engelbert Schucking and various other ones say no, they are anti-Machian solutions. And in particular, we can find model universes which rotate. They have vorticity. And in a universe model with vorticity, the inertial frame is not the same as the frame in which galaxies are fixed. That's basically the meaning of vorticity in a cosmological model. And many people would take that as a kind of knockdown thing to say, well, Mach's principle is not incorporated in all of general relativity. Then there was the search for non-singular matter solutions trying to fit with what Einstein was saying there, which I just mentioned. And just a brief byline on this. It is well known that loop quantum gravity has problems in producing the flat space-time limit. Well, from this viewpoint, that's a very good thing. That's exactly what the Machians would have wanted, that loop quantum gravity should not produce a locally flat space-time if there's no matter to generate it. Anyhow, from all of this, what I would believe, and what many people believe, what most people except Julian Barber believe, is that Machian solutions are a subset of all solutions of the Einstein equations characterized by particular boundary conditions. And for instance, Derek Rain published a book in which he said you need isotropy to get Mach's principle to work. So this is a very intriguing and difficult area in which there is still no consensus.
Yeah. part of the motivation for Machs Principle came out about this taste for Newton's absolute space and the ether, which Einstein did away with.
Yeah.
But on the other hand, in our time, we could say that the CBR is the ether and it defines absolute space.
Well,
so why do we still need that?
Well, I wouldn't quite say that. I mean, what you can say from a certain viewpoint is that the metric tensor is the ether, that the space-time itself is the ether. In a sense, it's a little like in quantum field theory, the vacuum isn't a vacuum. In general relativity or the space-time, it has a whole lot of structure, and you can, if you want, to use the label ether for space-time. Why not?
Yeah, so you're saying the metric itself, for example, can be the vacuum expectation value of some G, and that defines the ether.
Yeah.
In a more concrete sense, you might say that the GR generalization of Machs Principle is the space-time is defined not just by matter content, but also by gravitational radiation and other boundary conditions.
Yes.
Who would say that? You?
I think most relativists. That's the other boundaries. The three is gravitational radiation.
Mm-hmm.
What I want to say is that in the book by Barber and Pfister, which talks about this, there is something like 23 different formulations of Machs Principle. It's a highly controversial area. Now, where we do get something interesting for astrophysics is what has been established, and this goes back to Lenz and Tyrek, is when you have rotating shells of matter, they cause a dragging of inertial frames. And this is a very famous result from a long time ago, which has been looked at more recently. They also explain, in looking at the dragging of inertial frames, basically rotating shells out there communicate their rotations to nearer shell and make them also rotate. And this is basically the same kind of idea of what is happening there. They are, in fact, also expressed instantaneously. There's no light travel time involved, again, because it's happening on surface of constant time. And dragging effect is caused, again, even by matter outside the horizon. Lindenbell, Katz, and Bishak discuss this in recent papers. Spheres outside the horizon of a given angular momentum can cause a dragging around of shells inside the horizon. So again, like the cosmic background, you can feel more distant matter than we can see by its inertial dragging effects. And you'll find that in this paper, GRQC 0309126. So limits on such inertial dragging, again, means limits on the universe beyond the horizon. It's showing that in some sense, if we don't see such dragging, it means the universe outside the horizon is not rotating as a whole around us. Now, I was thinking about this and I did something which is wrong. I'm going to show you a wrong calculation because it's quite fun. I started thinking of the following. Supposing that the whole universe was rotating around us, that position, what would the effect be on the cosmic background radiation? Would it be an observable effect? So let's suppose the last scattering surface was rotating around us, about the Earth. Now, if it was rotating, then you would get the transverse Doppler shift and you get a quadrupole motion, a quadrupole anisotropy in the background radiation. And it's quite easy to see that this is the result you would get. It would depend on the angle in the sky, no effect this way, and maximal effect on the equator. So if the whole last scattering surface was rotating about it, then you would see a quadrupole in the in the microwave background because of the transverse Doppler effect. So, being a good Machian at that time, I said, wow, well, let's think of the following. This would be the same as having the background fixed and us rotating. This would be the same, obviously. And what this would mean, I got quite excited, was the idea as following. What this means is that if the universe was rotating, assuming now the universe is not rotating, but looking at a local rotating frame here, we could measure the rotation of this frame in terms